My name is Carlos Gaviria, and I recently graduated as PhD in software engineering from University College London, under the supervision of Earl Barr, Federica Sarro, and Mount Harlan. Today, I'll be presenting the paper we published in the New Trends and Ideas track of the Journal of Systems and Software. Software needs to scale to support an increasing number of users, and software development processes need to scale to support large distributed teams operating over complex code bases. Let's take the Linux kernel as an example. It has more than 13,000 contributors since 2015, adding around 10,000 lines of code daily. When operating at this scale, process problems can take precedence over technical ones, as seen in this quote from Linus Torvalds. The most widely adopted software processes come from the practitioner community and are based on decades of software engineering experience. In our paper, we complement this empirical approach by including mathematical models in the process improvement effort. When we mention mathematical models, we are referring specifically to game-theoretic ones. Roger Myerson, in the slide, defines game theory as the study of mathematical models of conflict and cooperation. It deals with the scenarios where rational, self-interested agents interact, and these interactions affect the agent's welfare. In game theory, these scenarios are called games, and the agents are called players. The game definition applies to card games like poker, but also to financial markets and international relations. Game theory can help us understand and even predict how players could behave when engaging in a game. Let's use an example to show how to apply game theory to a software development context. An organization hires 2 freelance developers to build a software system. Bob, who is in charge of developing the web front end, and Alice, who needs to develop the backend service. They both receive $50 upfront and an additional $50 when they deliver their component. For the systems to be finished, the organization also needs a REST API that manages communication between the backend and the front end. The development of this API requires the expertise of both Bob and Alice. When the API is ready, both developers could receive a bonus of $50. Also, if either Bob and Alice have time, they can pursue additional freelancer contracts for a value of $100. Now let's build a game theoretic model of this scenario. We consider Alice and Bob as the players. For the sake of simplicity, let's limit the actions they can perform to cooperate, represented by an upwards arrow, and to not cooperate, represented by a downwards arrow. In this game, by cooperation, we mean disposition to work together. The payoff table in this slide contains the pay of the player, given the action they perform. For example, the top left cell corresponds to the scenario where Alice and Bob cooperate. In that case, the system goes live and each receive $150. When neither cooperate, in the bottom right cell, they deliver their corresponding component without finishing the integration via the API. So each receive $100. When one freelancer cooperates but the other doesn't, the cooperating developer is not able to finish their component, obtaining only the initial $50, while the non-cooperating developer finishes their component and even has time to take an additional contract, pocketing $200. Behavior in game-theoretic models is defined in terms of strategies, where strategy assigns a probability to each action. Game theory provides insights on how rational players would behave in a game. At an optimal outcome, players adopt a strategy such that there are no incentive for deviating. We can obtain that outcome, also called a Nash equilibrium, processing the payoff table with an equilibrium algorithm. For this example, at equilibrium, both Alice and Bob adopt the same strategy, to not cooperate with a probability of 100%. At equilibrium, both freelancers obtain $100 with no incentive for deviation, since moving to cooperation would diminish their earnings in $50. This outcome is not good for the organization, since the system is not finished. It is also not good for the freelancers. If both cooperate, besides a happy client, they obtain more money. That's the dilemma behind this freelancer game. Although the organization and the freelancers could be in a better position if they cooperate, the software process behind the contract forces them to abandon cooperation. We believe that many software processes suffer from a similar problem, converging towards unwanted behavior at equilibrium. To address this issue, in our paper we proposed GetPy, a software process improvement approach based on game-theoretic models. GTPI stands for Game-Theoretic Process Improvement and is composed of 4 steps. In the first one, we identify a process anomaly, like the freelancer not cooperating. In step 2, we build a game-theoretic model of the process to improve, like the payoff table in the previous slide. Having the model ready, we can obtain its natural equilibrium and see if it matches the process anomaly identified in step 1. If that is the case, in step 3, we can use the game-theoretic model to experiment with process interventions. Once we have found an adequate process intervention, meaning its model shows the desired behavior at equilibrium, we proceed to the last step of GTPI and deploy and adopt the improved process. Next, let's explore how to use GTPI by addressing a software process problem reported by Lavallée and Robillard in their ICSI 2015 paper. In their paper, they describe a development team that found a problem in a software system. Building a permanent fix for this problem would take 20 person days, but building a temporal workaround would demand 5 person days. To avoid going over budget, this team opted for the workaround. The authors found that 12 other teams have faced the same problem before, and all those teams also choose for the workaround instead of the permanent fix. This scenario, which the authors call the budget protection issue, is problematic since developing a permanent fix is cheaper than developing 12 workarounds. Now that in step 1 we have identified a process anomaly, the budget protection issue, we can move to the empirical game design step. Game representations, like the payoff table, grow exponentially in size with the number of actions and players. In the Lavallée and Robillard paper, they observed 45 people distributed in 13 teams for around 10 months, so we need abstraction to keep a manageable game size. For this purpose, we propose to adopt empirical game-theoretic analysis, or EGTA. Reduced games produced by EGTA are also payoff tables, with the payoff values obtained via simulation. In EGTA models, the actions are limited to a set of strategies of interest. For our model of the budget protection issue, we consider the 2 developers as players, with a payoff as the number of features delivered per release. Our model has only 2 strategies. In a fix-intensive strategy, developers commit proper fixes until a week before the release, when they switch to commit kludges or workarounds. And a kludge-intensive strategy, where a developer switches to commit kludges when work items start accumulating. In the slide, for the table cell corresponding to a fix-intensive strategy against a kludge-intensive strategy, we use the process simulator to obtain the number of features delivered per developer. We do this over multiple iterations so we can calculate the averages. We select these 2 strategies arbitrarily for demonstration purposes. In a real setting, they should come from a dataset of the process to model. Building a process dataset is not trivial, considering that data might just not be there. For the budget protection issue, the code repository can be a source of commit behavior. But then we would need a way to differentiate commits for proper fixes from commits for kludges. As a proxy, we can use a static analysis tool like funbugs over commits. Or we can even apply NLP techniques to code review comments, or just ask the tech lead which behaviors they believe are relevant. Assembling the process dataset is an essential requisite for GTPI adoption. Now let's review the simulation model we use to obtain payoff values. Work items arrive at a given day according to I, where they can be picked by any developer available. The time developers spend on a work item depends if they choose to address it with a fix or a kludge. We want to reflect that kludges are faster to code than fixes. So fixes take 10% more time than T, the average resolution time, while kludges take 25% less than T. We expect kludges to be more likely to require rework, like bug fixing. So the probability of rework is 5% more than R, the average reward probability. For proper fixes, this probability is 10% lower than R. Kludges have a negative impact on code base quality. So every time a kludge is committed, the average resolution time increases in 5%. In a 2016 paper by me and Kung, they reported that in an Eclipse platform annual release, the average resolution time T is around 30 days, with an R of 7% for bug reopening. We plug these values in the simulator when we obtain payoff values. A step we skipped, but that is important when applying GetPy, is simulation model validation. We need to be certain that the simulation actually reflects the process to improve. There's an extensive literature in software process simulation. Here in the slide, we show one of the many validation approaches. We split the process dataset into 3 parts: training, validation, and testing. We use a training dataset to obtain simulation parameters, like the values of R, T, and I. The validation dataset is used for model calibration. Let's say that to ensure accurate payoff values, we want our simulation to predict the average number of features delivered per release. We obtain an estimate from the simulation model and compare it with the features released in the validation dataset. If they do not match, we would then need to improve the simulation design. We use the testing dataset for a final verification. Using the simulation, we obtain multiple samples of the target measure, like the number of features, and then compare it if they match what's observed in the testing dataset. This comparison can be done via hypothesis testing, confidence intervals, or even expert opinion. When the simulation model is ready, we can use it to populate the payoff table. After feeding the payoff table to a game solver like Gambit, we see that at equilibrium, both developers do the same, to adopt the clutch intensity strategy with 100% probability, matching what was reported by Lavallée and Robillard. We see that this payoff table shares similarities with the model generated for the freelancer dilemma. Both developers would deliver more features if they adopted the fixed intensity strategy, but this strategy is absent at equilibrium. Now that we confirm the software process anomaly, we can move to the third step of GetPy. We will use the game-theoretic model to explore potential solutions. An initial attempt would be to make kludges more expensive by making them more likely to require rework. We can try adopting post-commit analysis with an automatic tool like Findbugs that can detect problematic code. Let's assume that adopting such a tool would increase the rework probability for kludges from 1.05R to 2R. We built a new payoff table using the updated simulation model and use Gambit to obtain the behavior at equilibrium. Payoff values show that the clutch intensity strategy is now producing fewer features per release. But now we have 3 equilibria instead of 1. While in one, we have 100% probability for the fixed intensity strategy as desired. In the other 2, the clutch intensity strategy is still very dominant. Adopting automatic code analysis is beneficial, but we believe we can do better. Given the promising results obtained by increasing the cost of kludges, let's try go a bit further. If besides automatic code analysis, we include a code review made by an actual engineer, let's assume that the probability of reward for kludges increases from 2R to 5R. Here's the new payoff table using the updated simulation model. The equilibrium obtained is now aligned with what the organization wants, but developers adopt the fixed intensity strategy with a probability of 100%. While in the original process we obtained 18.12 features per release, in the new process at equilibrium we're delivering 19.58 features, an increase of 8%, while keeping a healthy code base. After evaluating this candidate process in the model, we now have some confidence to actually deploy it to the team. In our JSS paper, the goal was to introduce GetPy and show how we use game theory to reason formally about software processes. In a later publication in the Transaction of Software Engineering, we use GetPy to improve the prioritization of software tasks. Using game-theoretic models, we show that industry practices like bug triage are not effective, and we propose a new reputation-based process with truthful prioritization at equilibrium. If you're interested in this topic, please read this work. Besides the budget protection issue and task prioritization, we believe there are many other process problems that can be tackled with game theory. We invite you to use GetPy to improve software processes at your organization. Thank you very much for your time. And now I'm ready for questions.